Hello, and welcome to this edition of Amplitudes. My name is Kevin Schroeder, product marketer with Microchip Technologies Analog Division. This Amplitudes edition will cover the viewer-recommended topic of using amplifiers in current sensing applications. The need to closely monitor currents in today's electronics has increased over the years, as energy efficiency and safety have become major concerns. This video will focus specifically on the use of a shunt resistor to monitor current. For shunt-based current monitoring, the first question that must be addressed by a system designer is where to monitor the current. There are two basic options, high-side and low-side current monitoring. For high-side current monitoring, the shunt resistor is placed between the power supply and the load, as shown here. For low-side current monitoring, the shunt resistor is placed between the load and ground, as shown here. Both of these approaches have their pros and cons. High-side current sensing has the benefit of being able to detect current-related faults, such as a short circuit or an open circuit that could affect the load. Also, with high-side current sensing, the load can be referenced directly to ground, as we'll explore later. The main disadvantage of high-side current sensing is that the common mode voltage is relatively high, based on the supply voltage. Hence, a high common mode amplifier is required. As opposed to high-side current sensing, on the low side, the common mode is referenced to ground. Hence, a cheaper, more readily available, low-voltage amplifier can be used. As alluded to earlier, one disadvantage of low-side current sensing is that the shunt resistor is placed between the load and ground, which can cause ground loop issues since the load may not be at the exact same ground potential as the rest of the circuitry. As I mentioned earlier, for low-side current monitoring, essentially any single supply, low-voltage amplifier can work, as the common mode voltage is ground referenced. Selecting the best amplifier for this situation depends on price versus required performance, as the amplifier's offset voltage, offset drift, common mode and power supply rejection, and transient response may all be critical considerations. For high-side current sensing, the amplifier must be able to support the higher common mode range, as well as handle any voltage transients that may occur on the power line. A system designer can again use a standard operational amplifier configured as a difference amplifier, as shown here. However, there are some limitations to this approach. First, the input resistance is relatively low, determined by the external resistors, not to mention that the input currents aren't matched, which will limit the common mode rejection. Speaking of which, the common mode rejection will be limited by how well matched are the resistors, which leads to subpar performance. Due to these limitations, amplifier manufacturers have created specialty amplifiers for high-side current sensing, such as Microchip's PAC1921. These specialty amplifiers support high input common mode ranges while the core still runs off of a lower voltage rail, such as 3 volts or 5 volts, which simplifies the interface with lower voltage microcontrollers. This specialty device also provides a digital interface, providing voltage, current, and power information. The PAC1921 also supports an analog output for real-time data collection, making it an ideal solution for high-side current sensing. In summary, for shunt-based current sensing, the system designer has two basic choices, either high-side or low-side sensing, each with its own advantages and disadvantages. Which one is the best choice depends on the application. Thank you for joining me for this edition of Amplitudes. For more information, please visit www.microchip.com/linear. If you have a topic you would like reviewed in Amplitudes, please be sure to leave a comment below.